A force controlling the universe's fate remains completely invisible to us. This is dark energy, the greatest unsolved puzzle in modern cosmology. It makes the cosmos not just expand, but fly apart faster every second, and it constitutes about 68% of everything that exists. Yet we have no idea what it truly is. By the end of this exploration, you will understand the fierce battle between brilliant, competing theories trying to explain this cosmic phantom. Is it a strange new energy field, a sign our laws of gravity are wrong, or something even more profound? The answer will redefine reality itself. What do you imagine when you think of a universe shaped by the unknown? The year 1998 delivered a thunderclap that shattered a fundamental assumption about our cosmos. Two rival teams of astronomers, one led by Saul Perlmutter and another by Schmidt and Adam Riess, were engaged in a meticulous hunt. They were measuring the light from incredibly distant stellar explosions called Type 1, a supernova. These cosmic beacons are so predictably bright they act as standard candles, allowing scientists to gauge vast distances across space. By measuring how far away these supernovae were and how fast they were moving, the teams aimed to measure the universe's expansion rate and determine its ultimate fate. The prevailing wisdom was that the mutual gravitational pull of all matter in the cosmos would be putting a brake on this expansion, gradually slowing it down. The only question was whether that slowdown would eventually lead to a cosmic crunch or an eternal, gentle coasting. What they found instead sent a jolt through the scientific community. The most distant supernovae were significantly fainter than their models predicted. This meant they were much farther away than they should have been if the universe's expansion had been steadily decelerating. There was only one staggering conclusion possible. The expansion of the universe was not slowing down at all. It was speeding up. Some immense, repulsive force was actively pushing galaxies apart with ever-increasing strength. Imagine throwing a ball into the air, expecting it to slow, stop, and fall back down, only to watch it shoot upward faster and faster into the sky. That was the scale of the conceptual earthquake. This discovery earned the team leaders the Nobel Prize in Physics in 2011, but the award came with a profound admission of ignorance. They had discovered an effect, but not a cause. To name this mysterious, invisible driver of cosmic acceleration, scientists reached for the simplest placeholder, a label that openly confessed their bewilderment. They called it dark energy. Overnight, our picture of the universe's composition and destiny was turned inside out. Before 1998, cosmologists debated a universe dominated by matter, its future dictated by gravity. Afterward, they were forced to accept a cosmos where roughly 68% of everything is made of this unknown, anti-gravitational stuff. Dark energy was not a minor tweak, it was the dominant component of reality. It meant the universe's fate was not a grand collapse or a slow fade, but a runaway expansion leading toward an unimaginably cold, dark, and lonely end. The discovery solved no mysteries, it unleashed the greatest one of all. What unseen force commands the cosmos, accelerating its flight into the void? The quest to answer that question ignited a fierce and brilliant competition of ideas that continues to this day. Faced with this bewildering discovery, scientists needed a framework to make sense of it all. They turned to a model that had been waiting in the wings for decades, one that now became the cornerstone of modern cosmology. This is the Lambda cold dark matter model, often called the standard model of the universe. Its name holds the story of our cosmic ingredients. The cold dark matter, or CDM, represents the invisible scaffolding of the cosmos, the gravitational glue that holds galaxies and clusters together. But it is the first part, the Greek letter lambda, that holds the key to our accelerating fate. Lambda represents the cosmological constant, a mathematical term Albert Einstein introduced into his equations of general relativity back in 1917. He originally added it as a kind of fudge factor to force the equations to describe a static, unchanging universe, which was the prevailing belief at the time. When Edwin Hubble later discovered the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest blunder and removed it. The irony is profound. That same discarded idea was resurrected over 70 years later as the perfect candidate for dark energy. In the Lambda-CDM model, the cosmological constant is reinterpreted not as a mistake, but as a fundamental property of empty space itself. Imagine the vacuum of space not as a true nothingness, but as a seething quantum foam where virtual particles flicker in and out of existence. This activity, the theory suggests, endows empty space with a constant intrinsic energy density. And because this energy is a property of space, as the universe expands and more space comes into existence, more of this repulsive energy appears, driving the acceleration we observe. The power of the Lambda-CDM model is its breathtaking success. It is not just a wild guess, it is a precise mathematical framework that fits an astonishing variety of independent cosmic data like a key in a lock. It matches the subtle patterns in the cosmic microwave background, the afterglow of the Big Bang. It explains the distribution of galaxies across the vast cosmic web. It aligns with the observed abundances of light elements. By treating dark energy as this simple, constant lambda, the model provides a single number that makes our entire observable universe mathematically consistent. Yet this very success masks a profound and unsettling mystery. The cosmological constant works perfectly as a descriptive tool, a placeholder in our equations. But it tells us nothing about what dark energy actually is. We have given the phantom a name and a mathematical symbol, but we have not captured its essence. Why does empty space have this specific energy density? Why is its value so unimaginably tiny compared to what quantum field theory predicts, yet not zero? This discrepancy is one of the worst in all of theoretical physics. To simply call it lambda is to admit we have reached the edge of our understanding. The Standard Model is a magnificent map of the cosmos, but it points to a blank spot labeled "Here be dragons." This is the tension that fuels the scientific quest. With a phenomenologically successful model in hand, but no fundamental explanation for its most crucial component, researchers have been forced to venture beyond the map. They are now proposing radical alternatives, theories that seek to replace the placeholder with a real, physical mechanism. The competition to explain dark energy is not about minor tweaks, it is a battle for the soul of cosmology itself. This resurrected idea, the cosmological constant, now stands as the leading candidate for dark energy. Its story is a remarkable twist of scientific fate. In 1917, Albert Einstein was applying his revolutionary theory of general relativity to describe the entire cosmos. His equations naturally predicted a dynamic universe, one that should either be expanding or contracting. Yet the scientific consensus of the era, including Einstein's own belief, held that the universe was eternal and static. To force his equations to match this assumed reality, Einstein introduced a small, repulsive term, represented by the Greek letter lambda. This cosmological constant acted as a kind of anti-gravity, perfectly balancing the inward pull of matter to create a stable, unchanging cosmos. When Edwin Hubble's observations later proved the universe was indeed expanding, Einstein famously dismissed lambda as his greatest blunder, removing it from his equations. For decades, it was seen as a curious historical footnote, a cautionary tale against letting preconceptions dictate theory. The irony is almost poetic. The very term Einstein discarded to preserve a static universe was rediscovered as the engine of an accelerating one. Today's cosmologists have resurrected lambda, but with a profound reinterpretation. It is no longer an arbitrary fudge factor. Instead, it represents a constant energy density that is an intrinsic property of the vacuum of space itself. Think of empty space not as a true void, but as a quantum sea, constantly shimmering with activity. According to quantum field theory, so-called virtual particles and their antiparticles continuously pop into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This relentless quantum froth is believed to endow every cubic centimeter of space with a baseline energy, a background hum of existence. This vacuum energy, the theory goes, could be the physical manifestation of the cosmological constant. It would be a smooth, unchanging force woven into the fabric of reality, causing new space to have a built-in repulsive push. As the universe expands and more space is created, the total amount of this repulsive energy increases, driving the acceleration we observe. This elegant idea, however, crashes into one of the most severe problems in all of physics. When theorists calculate the expected energy density of the quantum vacuum, the number they get is catastrophically, unimaginably wrong. The predicted value is about 1 followed by 120 zeros larger than the tiny amount of dark energy we actually observe. To call this a discrepancy is a vast understatement. It is like predicting an ocean should exist in your coffee cup, but upon measuring, you find only a single, lonely molecule of water. This cosmological constant problem reveals a staggering gap between our two most successful theories, quantum mechanics and general relativity. It suggests we are missing something fundamental, either in how we calculate vacuum energy or in our very understanding of empty space. While lambda fits the observational data beautifully as a simple number in our equations, its proposed physical origin leads to a prediction so spectacularly incorrect that it leaves scientists deeply uneasy. The cosmological constant is a perfect placeholder, but a profoundly mysterious answer. This profound dissatisfaction is the catalyst that forces cosmology to look beyond its standard model, to consider possibilities where dark energy is not a constant at all, but something dynamic and strange. Dissatisfaction with a phantom constant has led physicists to propose a far more dynamic and alive alternative. This is the theory of quintessence, named for the ancient fifth element believed to fill the cosmos beyond earth, air, fire, and water. In this modern vision, dark energy is not a fixed property of empty space, but a new kind of field that permeates the universe, one that can change and evolve over time. Imagine the entire cosmos filled with an invisible, fluid-like substance, its density subtly shifting across billions of years. This is a scalar field, a concept familiar from the Higgs field that gives particles mass. But quintessence would be something entirely unique, a field whose energy acts as a repulsive force. To understand how it works, picture a ball resting on a hillside. The height and shape of that hill represent a potential energy landscape for the quintessence field. In the early, dense universe, the ball might be perched high up on a steep slope, its potential energy contributing to the cosmic expansion in one way. As the universe ages and expands, the ball begins to slowly roll down this hill. The speed of its roll and the changing steepness of the slope determine how the energy of the field behaves over time. This is the crucial difference from the cosmological constant. Lambda is like a ball sitting motionless at the very bottom of a flat, unchanging valley, its energy density forever constant. Quintessence is a ball still in motion, its energy density capable of increasing, decreasing, or even wavering as it traverses a complex terrain. This dynamic nature solves one of the deepest puzzles. Because the field evolves, its present-day energy density is not a random, finely tuned number, but the natural outcome of a long cosmic journey. Some models propose tracker fields, where quintessence automatically adjusts its energy to follow, and then eventually overtake the density of matter, elegantly explaining why dark energy only became dominant in the recent cosmic past. It transforms the mystery from a static number into a story, yet this narrative freedom comes at a cost. The shape of the hypothetical energy hill is not dictated by any known physics. It must be carefully chosen to match what we observe. Furthermore, if this field exists, it might not be completely silent. Could it interact with light or matter in subtle ways we have not yet detected? Could it even clump slightly, creating faint, ghostly variations in the repulsive force across the universe? Quintessence turns dark energy from a passive feature of space into an active, almost living entity with its own history and potential personality. It offers a compelling escape from the rigid confines of a constant, but in doing so, it opens a universe of new questions. If dark energy can change, what else about our cosmic fate remains unwritten? But what if the entire premise of this search is flawed? There is a third, profoundly radical school of thought that challenges the very foundation of the dark energy mystery. It asks a startling question: what if dark energy does not exist? What if the observed acceleration of the universe is not driven by a mysterious new substance, but is instead a colossal illusion, a sign that our understanding of gravity itself is wrong? This is the audacious proposition of modified gravity theories. Instead of inventing a new component to fill 70% of the cosmos, these physicists propose we revisit and revise the laws that have shaped our cosmic view for over a century. The most famous of these alternatives began with a different puzzle entirely. For decades, astronomers have noticed that stars at the outer edges of spiral galaxies rotate far too quickly to be held by the visible matter alone. The standard solution was to invoke dark matter, an invisible halo of particles providing extra gravitational glue. But in the 1980s, physicist Mordechai Milgram proposed a different fix. He suggested that perhaps Newton's law of gravity, and by extension Einstein's, breaks down in regions of extremely weak gravitational pull, like the fringes of a galaxy. His theory, called modified Newtonian dynamics, or MOND, successfully predicted many galactic rotation curves without needing any dark matter at all. This idea was later expanded into full relativistic theories like tensor vector scalar gravity, which attempted to rewrite Einstein's framework to incorporate MOND's effects. For a long time, this was a battle confined to the scale of galaxies, dark matter versus modified gravity. Then came the discovery of cosmic acceleration. Some theorists saw an opportunity for a grand unification. Could the same tweaks to gravity that explain galaxy rotations also account for the universe's expansion? Frameworks like F of R gravity emerged, where the familiar equations of general relativity are altered by making gravity a function of the curvature of spacetime itself. In these models, the fabric of the cosmos responds differently on the vast, empty scales between galaxy clusters than it does within them. The observed acceleration would not be a push from a new energy, but a subtle change in how spacetime stretches over cosmic distances. It is a breathtakingly economical idea. Instead of filling the universe with two invisible unknowns, dark matter and dark energy, you might explain both with a single adjustment to our most fundamental theory. But this elegance comes with a steep price. Modifying Einstein's theory of general relativity, which has passed every precise test for over a century, is an immense challenge. Any new theory must not only explain cosmic acceleration and galaxy rotations, but also perfectly reproduce all the successes of general relativity in our solar system, with binary pulsars and with gravitational waves. So far, no modified gravity theory has managed this complete feat without introducing severe conceptual issues or being ruled out by new observations. Yet the idea persists, driven by a powerful philosophical stance. It argues that before we accept that 95% of the universe is made of invisible, unexplained stuff, we should exhaust every possibility that the flaw lies in our equations, not in our senses of reality. This is not just a technical debate, it is a clash of scientific worldviews. Is the universe filled with hidden substances, or are we still missing the true geometry of the cosmic stage? Perhaps the most creative theories abandon familiar concepts of particles and fields altogether, and instead imagine dark energy as a kind of exotic cosmic fluid. These models venture into the realm of hypothetical substances with properties that seem to defy ordinary physics, all in an attempt to write a simpler, more unified story for the cosmos. One of the most fascinating proposals in this category is known as the Chaplygin gas. Picture a strange, smooth fluid filling all of space, but with a pressure that is not just negative, which is odd enough, but inversely proportional to its density. When this fluid is dense, its negative pressure is relatively weak. When it becomes diffuse, its negative pressure grows immensely strong. This bizarre property leads to a remarkable cosmic double life. In the early, compact universe, the Chaplygin gas would have been dense enough to clump together under gravity, behaving just like the dark matter that sculpts galaxies. Then, as the universe expanded and the fluid thinned out, its repulsive negative pressure would have taken over, driving the accelerated expansion we see today. In one elegant stroke, this single, exotic substance could potentially solve both of the universe's great dark mysteries. It is a theorist's dream of unification, replacing two unknown entities with one. Yet, like all such elegant ideas, it faces intense scrutiny. Could a single fluid truly mimic the precise, detailed behavior of both dark matter's gravitational scaffolding and dark energy's smooth repulsion across all scales of space and time? So far, detailed observations of the cosmic web and the cosmic microwave background have made it difficult for the simple Chaplygin gas model to match all the data, though more complex variants are still explored. This creative freedom extends even further into the speculative. Some models propose a form of phantom energy, a fluid with a negative pressure so extreme that it would cause the expansion rate to accelerate not just steadily, but uncontrollably to infinity. The end result of such a scenario is a cosmic finale called the Big Rip. In this distant future, the repulsive force would grow so strong that it would first tear apart galaxy clusters, then galaxies, then solar systems, and finally overcome the very forces holding atoms and nuclei together, dissolving the fabric of spacetime itself. While this is a mathematically possible outcome for certain equations, it remains a highly speculative edge of theory, not an observed certainty. What these exotic fluid models showcase is the incredible lengths to which cosmologists will go to solve this puzzle. They are willing to imagine substances with equations of state never seen in any laboratory, playing with the fundamental rules of pressure and density, all to account for the subtle tug and push recorded in the light of distant supernova and ancient radiation. It is a testament to both the depth of the mystery and the boundless creativity it inspires. If dark energy is real, it may be something far stranger than a constant or a field, something that challenges our very definition of a physical substance. The search for dark energy's identity leads us to the very edge of theoretical physics, to a realm where the fundamental ingredients of reality are not particles, but vibrating strings. This is string theory, and it offers not one single answer, but a staggering multitude of them. It paints a picture of a cosmos far stranger than we ever conceived, one that could fundamentally change how we ask the question of why. Within the mathematics of string theory, there is not one unique vacuum state, one single configuration of empty space. Instead, there is a vast landscape of possibilities, perhaps numbering 10 to the power of 500 or more. Each point in this landscape represents a stable universe with its own specific set of physical laws and constants, including its own value for the cosmological constant. In this dizzying perspective, our universe, with its specific, tiny, non-zero amount of dark energy, is just one possibility among an inconceivable number. So why do we find ourselves in this particular cosmic neighborhood? This is where a powerful and deeply controversial idea enters the conversation, the anthropic principle. In its simplest form, it suggests that the physical constants we measure are not necessarily the only possible ones. They are simply the ones compatible with the existence of observers like us. If the cosmological constant were vastly larger, the universe would have blown itself apart before galaxies could ever form. If it were negative and large, the cosmos would have collapsed long ago. In the string theory landscape, only a tiny fraction of possible universes have a cosmological constant small enough to allow for the slow growth of structure, the birth of stars, the formation of planets, and ultimately, life. We find ourselves in a universe with a peculiar value because we could not find ourselves anywhere else. This line of reasoning naturally expands into the concept of the multiverse. Imagine our observable universe not as all that exists, but as one bubble in an eternally inflating cosmic foam. New bubbles, each a separate universe with its own random set of physical laws drawn from the string landscape, are constantly popping into existence. In this eternal froth, every possible constant is realized somewhere. Our universe is not fine-tuned, it is simply one that won the cosmic lottery for habitability. This represents a profound shift in the explanatory framework. Instead of seeking a unique, dynamical mechanism within our universe that sets dark energy's value, the landscape and multiverse ideas attempt to contextualize it. The question changes from why is the cosmological constant this number, to why do we observe this number given our existence? For many scientists, this is a philosophically challenging proposition, as it moves explanations from testable, predictive physics into the realm of statistics and selection effects. Yet it remains a major line of thought, a direct attempt to grapple with the sheer improbability of our cosmic home. It suggests that the ultimate answer to the dark energy mystery may not lie in a new particle or field within our universe, but in understanding our universe's place within a reality of unimaginable breadth. The strangest theories often emerge at the intersection of seemingly unrelated fields. From the deepest principles of black holes and quantum information comes a proposal that reimagines dark energy not as a substance, but as a cosmic side effect of how reality stores data. This is the idea of holographic dark energy. It begins with one of the most mind-bending concepts in modern physics, the holographic principle. Traditionally, we think of information as being contained within a volume, like the data stored in a computer's memory chip. But studies of black holes revealed something astonishing. The maximum amount of information or entropy that a region of space can hold is not proportional to its volume, but to the area of its surrounding surface. Imagine a three-dimensional room where every detail, every object, every particle inside is perfectly encoded on the two-dimensional walls. The room itself is a projection of that boundary data. This principle suggests that our three-dimensional reality, with all its richness, might be a holographic projection from a two-dimensional surface at the edge of the universe. When applied to cosmology, this leads to a radical new take on the acceleration puzzle. If information is fundamentally tied to surfaces, then the energy density of the vacuum, dark energy itself, might also be governed by a boundary. Specifically, the density of dark energy in any cosmic region could be limited by the information capacity of that region's horizon, its ultimate boundary. One leading version of this theory links the dark energy density directly to the size of the future event horizon of the universe, the farthest distance any signal we send today could ever reach in the infinite future. In this view, dark energy is not a fluid or a field filling space. It is an emergent phenomenon, a consequence of the fundamental way the cosmos encodes and processes information. The acceleration we measure would be a macroscopic collective effect arising from the universe's total information budget, a kind of thermodynamic cost of doing cosmic business. This represents a profound synthesis weaving together threads from quantum gravity, black hole thermodynamics, and cosmology into a single, elegant, if highly speculative tapestry. It suggests that the answer to the greatest cosmic mystery might not be found by discovering a new particle, but by understanding the universe as a vast, dynamic information processor. The holographic principle asks us to consider that the true nature of reality might be written not in the volume of space, but on its skin, and that dark energy is simply the signature of that cosmic script. There is one more theory that questions not just our physics, but our very perspective. For over a century, cosmology has operated on a powerful simplifying principle, that on the largest scales, the universe is smooth. This cosmological principle states that if you zoom out far enough, matter and energy are spread evenly in every direction, with no special place or preferred center. It is this assumption of homogeneity and isotropy that allows us to apply Einstein's beautiful equations to the entire cosmos, treating it like a simple, expanding fluid. But what if this foundational smoothness is a convenient fiction that blinds us to the truth? A small group of theorists proposes exactly that. Their idea is called backreaction, and it suggests the accelerating expansion might be a grand cosmic mirage, born from our flawed way of averaging over a universe that is, in reality, profoundly lumpy. Think of the cosmos not as a uniform soup, but as a complex Swiss cheese. The dense, tightly curved regions are the cheese itself, the galaxies and clusters where gravity is king. The vast, underdense voids between them are the holes, regions of space that are nearly empty and expanding faster than the cosmic average. Now, when we observe distant supernova, their light travels through this bumpy, uneven landscape. According to the backreaction hypothesis, our standard models make a critical error. They assume we can simply take all this intricate structure, smooth it out into a uniform density, and plug that average into Einstein's equations to get the right answer for the universe's overall expansion. But gravity is not linear. The behavior of the whole is not simply the average of its parts when spacetime itself is warping in wildly different ways from place to place. The theory argues that as cosmic structures form over billions of years, the gravitational energy tied up in binding galaxies and clusters literally changes the way the overall fabric of space expands. The faster expansion of the giant voids begins to dominate the cosmic volume, while the light we observe is subtly affected by its journey through this uneven terrain. When we mistakenly apply the smooth model equations to this messy reality, we could get a result that looks exactly like an accelerating expansion, even though no mysterious dark energy is pushing from within. The acceleration would be an artifact, a misinterpretation stemming from applying the wrong mathematics to a complex, inhomogeneous universe. It is as if we tried to calculate the average speed of traffic by assuming every road was a straight, empty highway, completely ignoring the slowing effect of cities and towns. Our result would be wildly off, and we might invent a phantom force to explain the discrepancy. This is a deeply philosophical challenge. It forces us to ask whether the greatest mystery in cosmology is a problem of substance or a problem of measurement. Are we being fooled by the gap between the pristine simplicity of our equations and the tangled, structured reality they are meant to describe? While the backreaction hypothesis remains a minority view, and many detailed calculations suggest its effect is too small to fully explain the observed acceleration, its value is immense. It rigorously tests the limits of our most basic assumptions. It reminds us that sometimes before we invent new inhabitants for the cosmos, we must double-check the accuracy of our map. Could it be that the phantom we chase is not in the universe, but in the mirror of our own simplifying gaze? The most radical theories do not add new ingredients to the cosmos. They attempt to rewrite the recipe for gravity itself. This brings us to a truly paradigm-shifting idea known as emergent gravity, championed by physicist Eric Verland. What if gravity is not a fundamental force of nature at all? What if, like temperature or pressure, it is an emergent phenomenon, a collective behavior that arises from the interactions of countless microscopic parts? Think of a crowd in a stadium doing the wave. No single person is the wave. The wave is a property that emerges from their coordinated motion. In this view, the force we call gravity emerges from the complex entanglement and interactions of the fundamental bits of information that make up spacetime. This is not a minor tweak, it is a complete philosophical overhaul. It suggests that spacetime itself and the gravity that shapes it is not the starting point of physics, but the end result of a deeper, information-based process. So where does this leave the dark universe? In Verland's framework, dark matter and dark energy are not mysterious substances we have failed to detect. They are apparent effects, illusions that arise because we have been misinterpreting the elastic nature of emergent spacetime. Imagine the fabric of reality not as a static stage, but as a kind of elastic memory foam. When ordinary baryonic matter, the stars and gas we can see, sits in this foam, it creates a depression. But due to the elastic, emergent properties of the foam, the depression extends much farther out than the matter itself would suggest. From our perspective, it looks like there must be extra, invisible matter holding things together, creating the illusion of dark matter's gravitational pull. On the very largest cosmic scales, this elastic response of spacetime to the presence of matter and energy could also produce an apparent repulsive effect, a kind of cosmic spring back that mimics dark energy's accelerating push. The observed expansion of the universe in this picture could be a thermodynamic consequence, a reconfiguration of the cosmic information landscape as it evolves. This theory represents a breathtaking ambition. It seeks to derive the two greatest cosmic mysteries not from new particles or fields, but from the first principles of quantum information and statistical mechanics. It attempts to unify the phenomena of the dark universe under a single, elegant origin story, where the phantom is not a thing, but a behavior. While emergent gravity remains highly theoretical and faces significant mathematical and observational challenges, its value is profound. It forces us to reconsider the most basic assumptions about what is real and what is illusion in our cosmic map. It asks whether we have been searching for ghosts in a machine whose true workings we have yet to fully comprehend. Theoretical battles are ultimately settled by evidence, by the silent testimony of light that has traveled for billions of years. To distinguish between a constant lambda and a rolling quintessence field, between modified gravity and an exotic fluid, scientists need more than elegant equations. They need precise, multifaceted measurements of the universe's expansion history and growth. This requires an entire toolbox of cosmic observables, each probing a different facet of the dark energy puzzle. The first and most fundamental is the Hubble constant, denoted H0. This number represents the current expansion rate of the universe, the speed at which galaxies are receding from us at a given distance. It is the baseline against which all acceleration is measured, but a single snapshot is not enough. To understand if dark energy is changing, scientists must trace how the expansion rate has evolved over the full span of cosmic time. This is where the equation of state parameter, written as W, becomes crucial. Think of W as the personality profile of dark energy. It is the ratio of its pressure to its energy density. For Einstein's cosmological constant, W is exactly -1, a fixed and unchanging signature. For a dynamic field like Quintessence, W would be different from -1 and could vary over time. If W is less than -1, it could point toward phantom energy and a potential big rip future. Measuring W and tracking its possible evolution is the primary observational goal, the key to unlocking dark energy's true nature. A third, independent test comes from watching how cosmic structures grow. Gravity pulls matter together to form galaxies and clusters. A strong, repulsive dark energy acts against this clustering, suppressing the growth of the largest structures in the late universe. Modified gravity theories, however, often predict a different pattern of suppression. By mapping where and how matter clumps across the cosmos, we get a separate line of evidence that can confirm or contradict what the expansion history tells us. So how do we actually measure these abstract parameters? Astronomers deploy a powerful array of techniques, each a different way of reading the cosmic ledger. Type 1, a supernova, the original discoverers of acceleration, remain vital standard candles. By comparing their known intrinsic brightness to their observed faintness, we can measure vast distances directly, charting the expansion history across billions of years. Baryon acoustic oscillations provide a complementary method, acting as a standard ruler etched into the fabric of the universe. These are frozen sound waves from the primordial plasma, imprinting a preferred scale of about 500 million light-years into the distribution of galaxies. By measuring this scale at different cosmic epochs, we can chart the universe's geometry and expansion with extraordinary precision. Weak gravitational lensing offers a way to map the invisible. As light from distant galaxies travels toward us, it is subtly bent and distorted by the gravitational pull of all the matter, both dark and visible, in its path. By analyzing the shapes of millions of galaxies, we can reconstruct a three-dimensional mass map of the cosmic web, directly measuring how structure grows and how dark energy influences that growth. Finally, the cosmic microwave background serves as our foundational anchor, the pristine baby picture of the universe when it was just 380,000 years old. Its intricate temperature patterns encode the initial conditions, the amounts of ordinary matter, and dark energy, and the geometry of space. It sets the starting line for the entire cosmic race we are now observing. Each competing theory makes a distinct set of predictions for how these observables, the Hubble constant, the equation of state W, and the growth of structure, should behave from that ancient afterglow to the present day. The cosmological constant predicts a specific, unchanging track. Quintessence predicts a gentle drift. Modified gravity forecasts a different relationship between how the universe expands and how its structures form. The battle is fought in the painstaking analysis of petabytes of telescope data, in the subtle statistical tensions between measurements, and in the quiet hope that the universe will finally reveal which brilliant, desperate guess is correct. This elegant network of measurements has begun to reveal a subtle but persistent crack in our cosmic model. It is called the Hubble Tension, and it is one of the most intriguing anomalies in modern cosmology. At its heart is a simple, stubborn disagreement about a single number, the current expansion rate of the universe, known as the Hubble constant. We have two primary ways to measure it, and they are telling us two different stories. The first method looks back to the universe's infancy, to the cosmic microwave background. By analyzing the intricate patterns in this ancient light, scientists can deduce the universe's ingredients and geometry at that early time, and then use our standard Lambda-CDM model to predict how it should have evolved to the present day. This provides a late universe prediction for the Hubble constant. The second method measures the rate directly in our cosmic neighborhood, using luminous markers like Cepheid variable stars and Type 1, a supernova, as cosmic yardsticks to gauge distances and recession speeds of relatively nearby galaxies. These are direct observations of the current expansion. The problem is this: the value derived from the early universe and the value measured in the late universe do not agree. They disagree by a small but statistically significant margin, around 5 to 10%. It is as if you calculated how fast a car should be going based on its initial acceleration and the engine's power, only to look at the speedometer and find it reading consistently faster. This is not a simple measurement error. Multiple independent teams using different telescopes and different calibration stars have confirmed the late universe measurement. Meanwhile, the early universe prediction from the cosmic microwave background, most famously from the Planck satellite, is exquisitely precise. The gap persists. This Hubble tension suggests that our standard model of cosmology, the Lambda-CDM framework that has been so successful, might be missing a crucial piece of physics. It is an anomaly that cannot be easily smoothed over, and it has turned into a guiding light for theorists seeking to explain dark energy. Could resolving this tension point us toward the true nature of the cosmic accelerator? One promising direction involves giving dark energy a more active past. The standard model treats it as a constant, passive background. But what if dark energy was not always so quiet? A class of models known as early dark energy proposes exactly that. These theories suggest that a form of dark energy, or a dark energy-like field, was briefly active in the universe's first few 100,000 years before the formation of the first atoms. This temporary injection of repulsive energy would have subtly altered the physics of the primordial plasma, changing the size of the sound waves imprinted on the cosmic microwave background. That change would, in turn, affect the standard ruler we use to measure distances from that early epoch to now. By tweaking this early history, early dark energy models can adjust the predicted present-day expansion rate from the early universe, potentially bringing it into alignment with the directly measured late universe value. It is a compelling idea, a dynamic twist on the dark energy narrative that could solve two puzzles at once. Other theories, including certain types of evolving quintessence or interactions between dark energy and dark matter, also offer pathways to ease the tension. The very existence of this discrepancy is a powerful reminder that our cosmological model is a living document, not a finished textbook. Anomalies like the Hubble tension are not failures, they are the most precious signals we have. They are the universe whispering that there is something new to learn, a subtle clue etched into the fabric of spacetime itself. The search for dark energy's identity is now inextricably linked to the quest to heal this crack in our cosmic map, a process that may ultimately lead us to a deeper, more complete story of everything. At the heart of this great debate lies a single, crucial number. It is called the equation of state parameter, represented by the letter W. This unassuming symbol is the master key that could unlock dark energy's identity, the dividing line between a universe ruled by a simple constant and one animated by a dynamic field. To understand W, think of it as a personality test for the cosmos. It describes the relationship between the pressure dark energy exerts and its energy density. For the cosmological constant, Einstein's resurrected idea, the result is simple and rigid. Its W is exactly -1, a fixed and unchanging signature woven into the fabric of space itself. This constancy is its defining feature, a perfect flat line across the entire history of time. But for Quintessence, the rolling cosmic field, the story is different. Its W is typically greater than -1, meaning its pressure is slightly less repulsive. More importantly, this value is not locked in place. As the hypothetical field evolves, rolling down its energy landscape, W can slowly change over billions of years. The difference may seem subtle, a decimal point shifting in a complex equation, but its implications are cosmic. Detecting whether W is a perfect, eternal -1 or a drifting number is the ultimate observational goal. It transforms a philosophical preference into a measurable, physical fact. This is why monumental projects like the Dark Energy Survey dedicated years to mapping millions of galaxies, and why future missions like the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope are being built with such exquisite care. Their core mission is to measure W and its possible change over time with a precision we can only dream of today. They will employ all the tools in the cosmologist's kit, from weak gravitational lensing to baryon acoustic oscillations, building a three-dimensional movie of the universe's expansion and structure growth across 10 billion years. If these next-generation surveys finally pin down W and find it rock solid at -1, it would be a monumental victory for the cosmological constant. It would suggest that dark energy truly is a fundamental feature of the vacuum, as simple and immutable as the speed of light. But if they find a deviation, if the data insists that W is not -1, or better yet, that it has been changing over cosmic time, the entire landscape of theory would shudder. Such a discovery would be a fatal blow to the simple lambda model as a fundamental explanation. It would be a thunderous endorsement for a dynamic entity like Quintessence, proving that dark energy has a history, a life story written into the expanding cosmos. This makes the equation of state parameter the central battleground for the soul of modern cosmology. Every proposed theory, from exotic fluids to modified gravity, makes a specific prediction for what W should be and how it should behave. The coming flood of data from new telescopes will hold these predictions to the fire, deciding which brilliant guesses survive and which must be let go. The fate of our cosmic story will be decided not by elegance alone, but by the silent testimony of ancient light, measured one photon at a time. The universe's grandest structures hold a silent history. Spread across billions of light-years, galaxies are not scattered randomly. They form an immense, delicate web with dense clusters and filaments surrounding vast, empty voids. This cosmic web is a fossil record, a three-dimensional imprint of how gravity and dark energy have wrestled over time. To understand why, we must go back to the beginning. In the hot, dense early universe, tiny quantum ripples were stretched by inflation into minute differences in density. These seeds were everything. Over billions of years, gravity acted as a sculptor, relentlessly pulling matter toward these slightly denser regions. Ordinary matter, drawn by this pull, eventually ignited into the stars of galaxies, while dark matter provided the invisible scaffolding that shaped the overall pattern. The cosmic web we see today is the final masterpiece of this gravitational artistry, a direct descendant of those primordial whispers. But dark energy changes the story of this growth. As the dominant force in the recent cosmos, its repulsive push does more than accelerate expansion. It actively works against gravity's cohesive pull. Think of trying to build a sandcastle as the tide comes in. The rising water, like dark energy, makes it harder for the sand grains to stick together and form structures. In the cosmic sense, dark energy stretches the fabric of space, increasing the distances between concentrations of matter. This makes it more difficult for gravity to pull new material into existing clusters and filaments, effectively suppressing the growth of the largest structures in the universe. The later dark energy became dominant, the more time gravity had to build, and the more pronounced the cosmic web would be. The earlier it took over, the more it would have stunted that growth, leaving a sparser, more washed-out large-scale structure. This gives scientists a powerful independent test. Different theories of dark energy predict distinct signatures in this fossil record. A simple, constant cosmological constant suppresses growth in a specific, predictable way. A dynamic quintessence field, which might have been stronger or weaker in the past, would leave a different pattern in the clustering of galaxies. Even modified gravity theories predict a unique relationship between how the universe expands and how its structures form, a relationship that can be checked against the cosmic web. To read this fossil record, astronomers conduct massive redshift surveys. They use powerful telescopes to capture the light from millions of galaxies, measuring not just their positions on the sky, but their distances. They do this by measuring redshift, the stretching of a galaxy's light toward the red end of the spectrum caused by the expansion of the universe. The greater the redshift, the farther away and the further back in time we are observing. By combining millions of these measurements, scientists can construct a three-dimensional map of the cosmic web, revealing the voids, filaments, and clusters across cosmic time. Within this vast map, they search for a specific cosmic ruler called baryon acoustic oscillations. These are the frozen imprints of sound waves from the primordial plasma, a preferred scale of about 500 million light-years that was stamped into the distribution of matter. By measuring how this standard ruler appears at different epochs in the map, scientists can trace how dark energy has influenced the geometry and growth of structure with extraordinary precision. The subtle way dark energy has sculpted or failed to sculpt the grand tapestry of galaxies offers a testimony entirely separate from the light of distant supernova. It is a consistency check written across the heavens. If the story told by the expansion history aligns perfectly with the story told by the growth of structure, our model gains profound credibility. If they disagree, it is a clear signal that our understanding of the cosmic phantom is still incomplete, and that the true answer may be even stranger than we have dared to imagine. The silent testimony of ancient light is about to become a deafening chorus. A new generation of cosmic observatories, both in space and on the ground, is preparing to launch and open its eyes, armed with technology designed to do one thing: corner the phantom of dark energy. Their mission is to gather data on an unprecedented scale, providing the statistical precision needed to see the subtle signatures that have so far eluded us. At the forefront is the European Space Agency's Euclid spacecraft, a mission dedicated to mapping the geometry of the dark universe. Euclid will not look at a few thousand galaxies, but at billions. Its powerful telescope will conduct a massive survey, measuring the shapes and positions of galaxies across 10 billion years of cosmic history. It will use two primary techniques: weak gravitational lensing, to trace the distribution of dark matter by seeing how it warps the light of distant galaxies, and galaxy clustering, to measure the imprint of baryon acoustic oscillations, that cosmic ruler etched into the fabric of space. By combining these maps, Euclid will create the most precise three-dimensional chart of the universe's large-scale structure ever made, allowing scientists to measure with exquisite detail how dark energy has suppressed the growth of cosmic webs over time. Joining this hunt from a vantage point a million miles from Earth will be NASA's Nancy Grace Roman Space Telescope, with a field of view 100 times larger than that of the Hubble Space Telescope. Roman is built for cosmic speed dating. It will conduct sweeping wide-field surveys, capturing the fleeting light of thousands of distant Type 1 a supernova to trace the expansion history with new rigor. Simultaneously, its sharp vision will perform its own weak lensing survey, adding another independent, high-fidelity map of dark matter's distribution. The power of Roman lies in its sheer volume and speed, gathering a treasure trove of data that will let us compare the universe's expansion story with its structure growth story like never before. Any mismatch between these two narratives will be a glaring clue, pointing directly toward a dynamic dark energy or a modification of gravity itself. On a mountaintop in Chile, a ground-based behemoth will complement these space-based eyes. The Vera C. Rubin Observatory's legacy survey of space and time represents a different kind of power: relentless, all-seeing patience. Its enormous camera will image the entire southern sky every few nights for an entire decade. This will create a colossal, time-lapse movie of the cosmos, detecting billions of galaxies and tracking how their light changes. Within this avalanche of data, scientists will find millions of supernova for distance measurements, map the cosmic web in staggering detail, and even discover new, rare cosmic events that could serve as unexpected probes of dark energy. The LSST's strength is its comprehensiveness, watching the entire dynamic sky to catch any clue the universe deigns to show us. Together, these instruments represent a quantum leap in our ability to interrogate reality. They will collect orders of magnitude more data than all previous surveys combined. This immense statistical power is not about making a blurry picture slightly clearer. It is about revealing details we have never had the resolution to see. It will allow us to measure the equation of state parameter W and its potential drift over time with a precision that could definitively distinguish between a constant and a dynamic field. It could detect the subtle, telltale patterns that would confirm or rule out entire classes of theories, from exotic fluids to specific models of modified gravity. We are on the cusp of moving from an era of mystery into an era of measurement, where the universe's deepest secret may finally be forced into the light by the sheer weight of evidence. The phantom has had the cosmos to itself for billions of years, but its hiding places are about to be illuminated. The quest for dark energy forces us to confront a deeper question about the very nature of understanding. What does it truly mean to explain the cosmos? For centuries, the scientific ideal has been a clear, causal story. We see an apple fall and explain it with the force of gravity. We see stars shine and explain it with nuclear fusion. These are dynamical mechanisms, chains of cause and effect that satisfy our intuition for how the world works. A simple cosmological constant, lambda, fits the data, but it feels like a placeholder, a mathematical label for our ignorance rather than a true explanation of a force that commands the universe. It tells us the what, but pointedly refuses to answer the why. Our aesthetic desire is for elegance, for a beautiful equation that reveals a fundamental truth about the fabric of reality. Lambda is elegant in its simplicity, but that very simplicity can feel like an admission of defeat, a shrug in the face of a profound mystery. This tension pushes some of the most brilliant minds toward a radically different kind of answer. The multiverse and the string theory landscape represent a profound shift in the explanatory framework. Here, the question is not what unique mechanism in our universe sets dark energy's value. Instead, it becomes, why do we observe this value given our existence? In this view, our universe is not fine-tuned. It is simply one possibility among a near-infinite array. And we, as observers, can only find ourselves in a cosmos that allows for our existence. For some, this is a philosophically unsatisfying retreat from explanation. It exchanges a puzzle within our universe for a statistical necessity across an unobservable multitude. For others, it is the ultimate form of explanation, contextualizing our local laws within a grander, if untestable, reality. This debate cuts to the core of what science is for. Is its goal to provide a unique, causal narrative for everything we see, or is it to provide the most consistent and comprehensive account possible, even if that account includes inherent limitations on what we can ever know? The dark energy saga perfectly encapsulates the authentic, often messy, scientific process. It began with a stunning observation, the unexpected dimness of distant supernova. That observation demanded a theoretical explanation, leading to the resurrection of Lambda and the birth of rivals like Quintessence. Each theory then makes specific, testable predictions about the universe's expansion history and the growth of its structures. Now we are in the era of monumental testing, with telescopes like Euclid and Roman poised to gather the evidence that will confirm or shatter these ideas. This cycle rarely ends with a neat solution. More often, it leads to deeper, more profound questions. The discovery of cosmic acceleration did not solve a problem. it unveiled a deeper layer of mystery, one that may force us to revise our most fundamental concepts of space, time, and gravity. Ultimately, this search is about more than a missing component in our cosmic inventory. It is a journey into how we construct knowledge about the most fundamental aspects of reality. We are building an understanding of the universe from the inside, using the limited tools of mathematics and observation to infer the rules of a game we did not design. Every anomaly, every tension in the data is a precious clue. They are signs that our current map is incomplete, that the true territory of reality is stranger and more wonderful than we have yet dared to imagine. The value of the search may not lie solely in the final answer, but in the new vistas of thought and the unexpected connections it forces us to make along the way. What we ultimately discover about dark energy will not just tell us what fills the void. It will reveal something fundamental about our own place within the grand narrative of existence. This bizarre numerical mismatch is not just a small error, it is a screaming paradox. The cosmological constant problem stands as perhaps the most severe disconnect in all of physics. To grasp its depth, we must look closer at what quantum theory says empty space truly is. Forget the idea of a pure, silent void. According to quantum field theory, the vacuum is a turbulent sea of potential. Every known field, from the electromagnetic field to electron fields, is constantly active. So-called virtual particle-antiparticle pairs borrow energy from the vacuum, flickering into existence for an immeasurably brief moment before annihilating each other. This is not speculative, it is a tested part of our understanding with real effects like the Casimir force. The critical point is this: every single one of these quantum fluctuations contributes a tiny bit of energy to the vacuum. When you add up all the possible fluctuations from all possible fields across all possible energy scales, you get a number for the vacuum energy density. That number is astronomically, catastrophically large. It should be around 1 followed by 120 zeros bigger than the tiny amount of dark energy we actually observe from cosmic acceleration. To say our prediction is off by a factor of 10 to the 120th power is almost meaningless. It is the worst prediction in the history of science. If this theoretical vacuum energy were real, its repulsive gravity would have blown the universe apart in a fraction of a second after the Big Bang. Stars, galaxies, and life would have been impossible. Yet here we are, in a universe where the vacuum energy, or something mimicking it, is not zero, but is instead an almost imperceptibly small positive number. Why is it so exquisitely tuned? One proposed escape route comes from a beautiful symmetry called supersymmetry. In a perfectly supersymmetric universe, every known particle has a superpartner. The quantum contributions of a particle and its superpartner to the vacuum energy would be equal in magnitude but opposite in sign, perfectly cancelling each other out to give a net zero. The problem is, we do not live in that perfect universe. If supersymmetry exists in nature, it is a broken symmetry. The superpartners, if they are real, must be much heavier than their ordinary counterparts, meaning the cancellation is imperfect. A huge amount of vacuum energy is left uncancelled, thrusting us right back into the heart of the fine-tuning crisis. This leaves physicists with deeply uncomfortable alternatives. The first is that we are missing a complete theory of quantum gravity, a framework that seamlessly merges the quantum world with general relativity. In such a theory, the rules for calculating vacuum energy might be fundamentally different, perhaps rendering our current naive summation meaningless. The other alternative, as we have seen, is the anthropic or multiverse reasoning. In a landscape of perhaps 10 to the 500 possible universes, each with a randomly assigned cosmological constant, only those with a value incredibly close to zero could ever form galaxies and stars and planets capable of hosting observers. We find ourselves in such a universe not because of a dynamical mechanism, but because it is the only type of universe we could possibly find ourselves in. For many scientists, this feels like a surrender, an abandonment of the quest for a causal, mechanical explanation rooted in the laws of our one universe. This extreme fine-tuning is not a minor puzzle. It is the engine driving the most radical theoretical innovation. It is the relentless whisper that our map of reality is missing a continent. Every proposal, from dynamic fields to emergent gravity, is in part an attempt to solve this one profound riddle. Why does our cosmos balance on such a razor's edge between a catastrophic rip and a lifeless crunch? The answer, when it comes, may not just explain dark energy, it may redefine the very nature of physical law. Perhaps the two great phantoms of the cosmos are not strangers at all. For all their differences, dark matter and dark energy share a profound commonality. They are both invisible, dominant, and unexplained. This has led theorists to a compelling and deeply interconnected possibility. What if these two shadows are whispering to each other? The concept is known as interacting dark energy, and it proposes that the dark sector is not a collection of isolated entities, but a coupled system where energy can flow between its mysterious components. In this vision, dark energy is not a solo actor on a static stage. It is engaged in a continuous, cosmic conversation with the dark matter that sculpts the galaxies. Think of it as two vast reservoirs connected by a hidden pipe. As the universe evolves, energy could slowly transfer from one to the other, altering their respective densities in a dynamic dance. In some models, dark energy decays into dark matter, gently feeding the gravitational scaffolding of the cosmos over time. In others, the flow reverses, with dark matter providing the source for the repulsive force. This interaction rewrites the standard evolutionary story. In the Lambda-CDM model, dark matter density dilutes predictably as the universe expands, while dark energy density remains constant. Their ratio, therefore, changes dramatically across cosmic history. The fact that we happen to live in an epoch where their densities are roughly comparable has always seemed strangely coincidental, like catching two trains from different stations at the exact moment they pass each other. Interacting models can naturally explain this apparent timing. By allowing an energy exchange, the theory can engineer a scenario where the densities of the two dark components evolve in tandem, keeping them in a similar ballpark for a significant stretch of cosmic time. This solves the so-called coincidence problem not by fine-tuning, but by introducing a physical link. The observational signatures of such a hidden dialogue would be subtle but potentially detectable. One key signal would be a deviation in how cosmic structures grow. Dark matter's gravitational pull is the engine of structure formation. If dark energy is actively draining energy from it, that engine could lose power earlier than expected, suppressing the formation of galaxy clusters in a unique pattern. Conversely, if dark matter is feeding dark energy, the accelerated expansion might kick in with a different timing or intensity than the simple cosmological constant predicts. These imprints would be sought in the same detailed maps of the cosmic web and the clustering of galaxies that next-generation surveys are meticulously creating. The beauty of this idea is its unifying ambition. It acknowledges that our two greatest unknowns might be two sides of the same enigmatic coin, different manifestations of a single, complex dark sector whose internal rules we have yet to decipher. It transforms the cosmic landscape from a stage with independent actors into an interconnected ecosystem, where the fate of one phantom is inextricably tied to the behavior of the other. This makes the universe feel more relational, more dynamically woven together, even in its darkest, most unseen realms. Among the many possible futures written in the equations, one stands out for its sheer, dramatic finality. It is the domain of phantom energy, a hypothetical form of dark energy so extreme it would not merely accelerate the universe, but unravel it from the inside out. This scenario hinges on a single critical detail in the equation of state, the parameter W. For the cosmological constant, W equals -1. But if dark energy were a phantom, its W would be less than -1. This small mathematical shift has a monstrous physical consequence. Instead of the energy density of dark energy remaining constant as space expands, it would actually increase over time. The more the universe grows, the stronger this repulsive force becomes, which makes the universe expand even faster, which in turn makes the force stronger still. It creates a runaway feedback loop of acceleration, a cosmic engine spiraling toward infinity. The end result of this unchecked escalation is a theoretical finale known as the Big Rip. Imagine the expansion of space itself growing so fierce that it ceases to be a gentle stretching and becomes a violent, overwhelming force. The first structures to succumb would be the largest bound by the weakest gravity. Galaxy clusters, those immense cities of stars, would be the first to be pulled apart, their member galaxies flung into the endless, growing void. Next, the expansion's grip would tighten on individual galaxies. The Milky Way and all its stars would be scattered, their gravitational bonds shattered. Then it would reach into solar systems. Stars would be torn from their planets, and planets themselves would be pulled into fragments. As the phantom force continues to amplify, it would eventually overcome the forces that hold matter together. The relentless stretching of space would overcome the electromagnetic bonds holding molecules and atoms intact, dissolving every solid object into a chaotic soup of subatomic particles. In the final moments, even atomic nuclei would be ripped apart, and space-time itself would be shredded beyond recognition. It is the most absolute end conceivable, a dissolution of the very fabric of reality. While this is a mathematically consistent possibility within certain models, it is important to recognize its speculative nature. Current observational data from supernova, the cosmic microwave background, and large-scale structure surveys all point to a value of W that is very close to -1, consistent with a simple cosmological constant. The phantom energy scenario, with its W less than -1, currently lies at the far edge of the uncertainty in our measurements. It has not been ruled out definitively, but it is not supported by the evidence we have. Yet its value is profound, far beyond its likelihood. The Big Rip serves as a dramatic, visceral reminder that the nature of dark energy is not an abstract academic exercise. The precise value of that one parameter, W, is not just a number in an equation. It is the key that unlocks a prediction for the ultimate fate of everything we see: the stars, the planets, and the very atoms that make us. It frames our scientific quest in the most human terms possible. We are searching the cosmos not just to understand its beginning, but to learn how our story ends. The most profound theories for dark energy brush against the ultimate frontier of physics. They are not just about a new substance, but about rewriting the rules of reality at its most fundamental level. This places the entire mystery at the precipice of an even greater quest, the search for a theory of quantum gravity. For a century, physics has been split into two magnificent but incompatible kingdoms. General relativity masterfully describes the cosmos on the grandest scales, the warping of space-time by stars and galaxies. Quantum mechanics, with equal brilliance, governs the bizarre, probabilistic world of atoms and subatomic particles. Yet these two pillars of modern science refuse to speak the same language, unifying them into a single, coherent framework. A theory of quantum gravity is arguably the greatest unsolved problem in all of physics. The tantalizing and deeply frustrating truth is that many of the most elegant explanations for dark energy, from string theory landscapes to emergent gravity, are born from attempts to build this very unification. They are predictions or side effects of a deeper reality we have not yet fully grasped. This creates an immense and ironic challenge. We are trying to use the large-scale, low-energy phenomena of cosmology, the gentle stretching of space over billions of years, to test ideas that live in the realm of the unimaginably small, dense, and energetic, like the first moments after the Big Bang. It is akin to trying to deduce the detailed laws of nuclear fusion by carefully watching the gentle sway of a tree in the wind. The quantum gravitational effects on cosmic acceleration are expected to be vanishingly subtle, whispers of a microscopic world echoing across the cosmic void. The problem is compounded by an issue physicists call degeneracy, a slight, observed tweak in the expansion history, a tiny anomaly in the growth of structure, could be explained by a dynamic quintessence field, a modification of gravity, an interaction in the dark sector, or a signature of quantum gravity. These completely different theoretical origins can produce nearly identical observational fingerprints at our current level of precision. The map of possible explanations is filled with overlapping territories, making it extraordinarily difficult to pinpoint which path is the true one. This is the chasm between elegant theory and empirical proof. A beautiful mathematical construct from string theory might suggest a specific range for the cosmological constant, but verifying that it, and not a simpler, mundane alternative, is the correct answer requires a level of observational discrimination we are only now approaching. The dark energy puzzle, therefore, forces innovators to become cosmic detectives, searching for clever, indirect signatures. They look for unique patterns in the polarization of the cosmic microwave background that only certain quantum gravity models would imprint. They analyze the clustering of galaxies at the very largest scales for statistical anomalies that could hint at spacetime being granular or pixelated at a fundamental level. They even propose that precise measurements of gravitational waves from merging black holes could reveal subtle deviations from Einstein's predictions, a backdoor into quantum gravitational effects. In this way, the phantom driving the universe apart becomes a unique probe. It turns the entire cosmos into a laboratory for testing laws of physics that operate at energies far beyond anything we can ever recreate on Earth. The search for dark energy's identity is no longer just a chapter in cosmology. It is a daring experiment at the crossroads of the very large and the very small, where the ultimate fate of the universe may hinge on understanding the quantum structure of spacetime itself. History offers a profound echo in the search for dark energy, a reminder that today's greatest mystery often mirrors the puzzles of the past. In the late 19th century, physicists were convinced that light waves, like sound or water waves, needed a medium to travel through. They named this hypothetical substance the luminiferous ether, an invisible, frictionless fluid that was thought to permeate all of space, providing the stage upon which light performed its dance. It was a logical and elegant solution born from the best understanding of the time. The ether was not seen as a wild guess. It was a necessary component of a coherent physical world, much like dark energy feels to us today. Then came an experiment that would shake the foundations of physics. In 1887, Albert Michelson and Edward Morley designed an incredibly sensitive apparatus to detect the ether wind, the subtle drag expected as Earth moved through this cosmic medium. Their result was stunning and deeply unsettling. They found nothing. No ether wind, no detectable medium at all. Light traveled at a constant speed regardless of direction or the planet's motion. This null result was a crisis, a beautiful theory shattered by stubborn data. It created the intellectual vacuum that a young patent clerk, Albert Einstein, would fill with his theory of special relativity, which discarded the ether entirely and redefined space and time. The parallel to our current moment is striking. Dark energy is our modern ether, a placeholder name for a gap in our understanding. It fits the data beautifully within our current model, the Lambda-CDM framework, just as the ether once fit the wave theory of light. But the haunting question lingers: is dark energy a genuine new facet of physical reality, a true component of the cosmos we must learn to understand? Or is it, like the ether, a conceptual crutch that will be swept away by a future revolution, perhaps a theory of quantum gravity that rewrites the rules from the ground up? The history of the ether teaches two crucial lessons. The first is humility. The most intelligent scientists of an era can be collectively convinced of something that later proves to be a mirage. Their assumptions, however logical, can blind them to a deeper truth. The second lesson, however, is one of triumph. The dismantling of the ether was not a defeat for science, it was its greatest victory. It cleared the path for a far more profound and accurate description of reality. The mystery became the catalyst for a leap in understanding. This is the delicate tension we now inhabit. We must take dark energy seriously as the best explanation we have, while holding it lightly, ready to abandon it the moment a better, more coherent theory emerges from the data. The next Michelson-Morley experiment for dark energy may already be underway, in the form of the Hubble Tension, or a subtle anomaly in the growth of cosmic structure. It might be a single, crucial measurement from the Euclid or Roman telescopes that simply cannot be reconciled with a constant lambda. That moment of contradiction, should it come, will not be a crisis to fear, but an opportunity to embrace. It would be the signal that we are on the verge of a new relativity, a conceptual shift that will once again redefine our place in the cosmos. The phantom we chase may ultimately be the shadow of our own incomplete understanding, waiting for the right light to reveal its true shape. This cosmic detective story is often clouded by the very language we use to describe it. The term dark energy itself can conjure up images of a sinister, supernatural force, a cosmic villain lurking in the void. But in science, dark simply means unseen. Dark energy does not glow, reflect, or absorb light. It is invisible to our telescopes not because it is evil, but because it does not interact with the electromagnetic force in any way we have yet detected. It is a phantom of observation, not of intention. It has no mind, no purpose, no malice. It is simply a property of the cosmos that behaves according to physical law, and our task is to read that law in the light of distant stars. Another common mix-up lies in the name's closest cousin. Dark energy is not the same as dark matter. While both are invisible and dominant, they play entirely different roles in the cosmic play. Dark matter is the sculptor. It clumps together under gravity, forming the invisible halos that galaxies spin within, and the vast scaffolding of the cosmic web. It pulls things together. Dark energy, in stark contrast, is the stretcher. It is smooth, not clumpy, and its effect is to push things apart on the largest scales. They are two separate mysteries with distinct signatures, and solving one does not automatically solve the other. Think of them as the two great unknowns in a cosmic budget. One provides the gravitational glue, the other provides the repulsive push. This repulsive nature also leads to a tempting but inaccurate label. It is easy to call dark energy a form of anti-gravity. The problem is that phrase suggests a force that actively cancels or opposes gravity everywhere, like a magnet repelling its opposite pole. That is not what we see. Within our solar system, within galaxies, gravity reigns supreme, completely unaffected. Dark energy's repulsive effect only becomes dominant in the vast, nearly empty expanses between galaxy clusters. A more accurate description is that dark energy is a property of space itself that causes new space to have a built-in, gentle repulsive tension. It is not fighting gravity locally. It is changing the background fabric upon which the drama of gravity plays out. With so much uncertainty, it might seem like scientists are just taking wild guesses, inventing fanciful stories to cover their ignorance. Nothing could be further from the truth. Every theory, from the cosmological constant to quintessence to modified gravity, makes specific, testable predictions. and those predictions are confronted by an avalanche of data from monumental observational campaigns. We are not guessing in the dark. We are surveying the cosmos with instruments of breathtaking precision, mapping billions of galaxies, timing the flashes of dying stars, and analyzing the fossilized light from the universe's infancy. The process is slow, meticulous, and deeply evidence-based. It is a collective effort of thousands of minds, checking and rechecking each other's work, where ideas survive only if they can withstand the relentless scrutiny of reality itself. Clearing away these misconceptions does more than just set the record straight. It empowers you to see the search for what it truly is, one of the most ambitious and rigorous detective stories ever undertaken. It is not a tale of supernatural forces or random speculation. It is a nuanced, challenging, and profoundly human attempt to read the clues the universe has left for us, written in the subtle dimming of ancient starlight and the grand architecture of everything that exists. The mystery is real, but so is the meticulous, awe-inspiring science trying to solve it. Behind every elegant equation lies a universe of chaotic, non-linear complexity that no human mind can solve alone. This is where the quest moves from chalkboards to silicon, from theory to simulation. To test which phantom might rule our cosmos, scientists build entire universes inside the world's most powerful supercomputers. These are not simple animations, they are colossal numerical experiments known as n-body simulations, and they are the proving grounds where theories of dark energy face a virtual reality check. The scale is almost incomprehensible. A typical simulation might begin with a virtual box representing a chunk of the early universe, populated by billions, even trillions, of individual particles representing dark matter. Each particle feels the gravitational pull of every other particle, a calculation that would take millennia on a desktop computer. Supercomputers, with their hundreds of thousands of processing cores working in parallel, perform these astronomical calculations in months or weeks. They apply the laws of physics, including a specific model for dark energy, and then let the simulation run, fast-forwarding the evolution of this digital cosmos over billions of virtual years. You can watch as gravity sculpts the primordial soup, pulling matter into filaments and knots, birthing galaxies and clusters that spin and merge in a dynamic cosmic web. The final output is a detailed, three-dimensional map of a fully grown, synthetic universe, but the true power lies in comparison. Researchers generate not one, but many such universes, each governed by a different rulebook. One simulation might use Einstein's cosmological constant, another a rolling quintessence field, a third a specific model of modified gravity. They then take these virtual skies and subject them to the same analysis that astronomers perform on the real night sky. They measure the clustering of their simulated galaxies, the statistics of their voids, the subtle distortions from weak gravitational lensing. They ask a simple, profound question. Which simulated universe, born from which theoretical seed, most closely resembles the one we actually inhabit? This process transforms abstract mathematics into a statistical contest. It allows scientists to explore the consequences of theories that are far too complex for pen and paper solutions, where the gravitational dance of billions of particles creates emergent patterns no equation can predict in advance. These simulations reveal the subtle signatures that different dark energy models imprint on the large-scale structure of the cosmos. A constant lambda produces a specific pattern of galaxy clusters. A dynamic quintessence might create a slightly different distribution of cosmic voids. Modified gravity could leave a unique fingerprint in the way filaments of the cosmic web connect. By running these digital experiments again and again, cosmologists can rule out entire families of theories whose virtual universes look nothing like our own. It is a form of numerical alchemy, turning speculative ideas into concrete, testable predictions, Without these synthetic universes, we would be theorizing in the dark. The supercomputer's virtual cosmos acts as a crucial bridge, a laboratory where the invisible laws governing dark energy are forced to reveal their hand in the visible architecture of everything. The universe speaks in more than just light. To truly corner the phantom of dark energy, we must learn to listen to its other voices, the faint whispers carried not by photons, but by the most elusive particles and the ripples in spacetime itself. These alternative data streams promise to break the stalemate between competing theories by offering entirely new ways to measure the cosmos. The first of these ghostly messengers has been streaming through you since the moment you were born. They are cosmic neutrinos, trillions of which pass through your body every second without a trace. A vast sea of these particles, known as the cosmic neutrino background, was forged in the first second after the Big Bang, and it still permeates all of space. While we cannot detect this primordial sea directly yet, its presence has a subtle, calculable effect on the universe's development. These relic neutrinos, moving at nearly the speed of light, helped smooth out the early universe and influenced how the first structures began to clump together under gravity. By measuring the detailed patterns in the cosmic microwave background and the large-scale distribution of galaxies with extreme precision, cosmologists can infer the properties of this neutrino background. This, in turn, provides an independent check on the expansion history of the universe during those primordial epochs, offering another constraint to pin down the behavior of dark energy across time. It is a shadowy imprint, a fossil record written not in light, but in the most penetrating particles known to physics. An even more revolutionary new sense is now online, the direct detection of gravitational waves. These are not waves of light or matter, but literal ripples in the fabric of spacetime, predicted by Einstein and finally observed in 2015. When massive objects like black holes or neutron stars spiral together and merge, they shake the cosmos, sending out these ripples at the speed of light. For dark energy research, a specific type of merger is the Holy Grail, the collision of two neutron stars. Why is this event so special? Because it is what astronomers call a standard siren. Think of it like this. When you hear an ambulance siren, the pitch tells you how fast it is moving toward or away from you. A gravitational wave from a merging neutron star binary works in a similar way. The shape of the gravitational wave signal we detect reveals the intrinsic strength of the event, how much spacetime was actually warped. From that, scientists can calculate the true distance to the merger with remarkable accuracy, completely independent of the traditional cosmic distance ladder of Cepheid stars and supernova. It is a direct ruler etched into the fabric of reality. The true power unlocks when we catch the same event with both ears and eyes. When two neutron stars collided in a galaxy called NGC 4993 in 2017, observatories detected the gravitational waves. Then, telescopes around the world and in space swiveled to capture the brilliant flash of light across the electromagnetic spectrum, from gamma rays to radio waves. This electromagnetic counterpart pinpoints the host galaxy, allowing us to measure its redshift, the stretching of its light that tells us how fast the universe is expanding at that distance. For the first time, we had a direct one-step measurement, a known distance from the gravitational wave siren paired with a recession speed from the light. This single event provided a fresh, independent measurement of the Hubble constant, the universe's current expansion rate. As we detect more of these multi-messenger events from greater and greater distances, they will map the expansion history of the cosmos with a new, pristine clarity. Each standard siren is a data point free from the calibration uncertainties that plague other methods, offering a clean test of how dark energy has influenced the stretching of space across billions of years. This new window, where we feel the ripples of spacetime and see the fiery aftermath, promises to cut through the degeneracies that confuse our models. It is a completely different language from the universe, one that may finally allow us to hear the true story of the cosmic phantom. The timeline of the cosmos stretches over 13.8 billion years, yet we find ourselves in a breathtakingly narrow window of cosmic coincidence. For the overwhelming majority of that history, the universe was a dramatically different place. In the first several billion years, the energy density of matter, both dark and ordinary, was utterly dominant. Space was dense, crowded, and expanding under the heavy pull of gravity's deceleration. Then, as the universe grew and thinned out, the tide began to turn. Roughly 5 billion years ago, the scales tipped. The repulsive push of dark energy finally overcame the gravitational pull of matter, and the cosmos entered its current phase of runaway acceleration. What is so strange about this moment is not that it happened, but that we are here to witness it. The period where the energy densities of dark matter and dark energy are within an order of magnitude of each other is a fleeting sliver of cosmic time. For eons before, matter dominated by a colossal margin. For the infinite future ahead, dark energy will reign supreme, its influence growing as everything else dilutes toward nothing. We exist in the brief transitional moment where the two great unknowns are in a kind of balance. This is the coincidence problem, and it asks a deeply unsettling question. Why now? Why do conscious observers find the universe in this peculiar, temporary state? If the value of the cosmological constant were just slightly different, this epoch of rough equality could have occurred impossibly early, before galaxies formed, or so far in the future that all stars had long since burned out. It feels like another layer of exquisite fine-tuning, as if the universe's parameters were set not just to allow life, but to ensure that life arises precisely at this special crossover point. For many scientists, this apparent coincidence is too glaring to ignore. A truly satisfying theory of dark energy should not just explain what it is, but also why its dominance began at this specific chapter in the cosmic story. This demand has directly shaped some of the most compelling alternative models. Certain versions of Quintessence, known as tracker fields, are designed specifically to address the why now question. In these models, the dark energy field does not have a random initial value. Instead, its energy density automatically tracks or follows the dominant energy component of the universe, whether it was radiation in the very early cosmos or matter later on. The field bides its time, lying in wait. Then, as the universe expands and the density of matter falls below a critical threshold, the tracker field naturally breaks free and begins to dominate, steering the universe into acceleration at roughly the epoch we observe. There is no fine-tuning of initial conditions. The dynamics of the field itself guarantee the timing. Similarly, interacting dark energy models offer another elegant solution. If dark energy and dark matter are in a slow conversation, exchanging energy, their densities can evolve in a coupled way. This linkage can orchestrate their rise and fall so that they remain comparable for a significant stretch of cosmic time, making our current epoch not a bizarre accident, but a predictable and extended phase in a long cosmic relationship. Solving the coincidence problem is often seen as a key marker of a mature theory. It moves an explanation from merely fitting the data to providing a deeper narrative, one where the story of the universe feels inevitable, not arbitrarily staged. The fact that we are here in this brief moment of balance may be the universe's most subtle clue, a hint that the phantom we chase is not a static number, but a player in a dynamic, unfolding plot with its own intrinsic sense of timing. The ultimate ambition of cosmology is not to catalog mysteries, but to weave them into a single story. This drive leads to one of the most profound unification dreams, the possibility that dark energy is not a new actor, but an old one returning for a final act. Its partner in this cosmic reunion is inflation, the theory that a fraction of a second after the Big Bang, the universe underwent a burst of hyper-accelerated expansion, smoothing and flattening the cosmos to create the conditions we see today. On the surface, the two events could not seem more different. Inflation was unimaginably violent and brief, an explosive growth spurt that lasted perhaps a trillionth of a second, driven by energies trillions of times greater than those in today's particle accelerators. Dark energy, by contrast, is a gentle, persistent push, operating at an energy scale so tiny it defies comprehension, and it has been active for billions of years. Yet at their heart, they share a stunningly similar signature, a period where a mysterious, dominant form of energy causes the very fabric of space to expand at an accelerating rate. This tantalizing parallel has led theorists to ask a breathtaking question. Could inflation and dark energy be two faces of the same fundamental phenomenon? Could a single kind of entity, perhaps a scalar field like the one proposed for Quintessence, have been responsible for both epochs? In this grand narrative, the field would have been incredibly energetic in the universe's first instant, driving the frantic expansion of inflation. As the universe cooled, the field would have settled into a dormant state, its energy latent and negligible for eons. Then, as the cosmos expanded and thinned out over billions of years, the conditions might have shifted just enough for this sleeping giant to stir once more, reawakening with a faint whisper of its former power to drive the late-time acceleration we call dark energy. It is an elegant and deeply satisfying vision, a single cosmic character with a dual role, responsible for both the breathtaking beginning and the unfolding fate of everything. The challenges to this beautiful idea, however, are as vast as the cosmic scales it tries to bridge. The energy difference between the inflationary field and the proposed dark energy field is not just large, it is perhaps the largest discrepancy in all of nature, requiring an explanation for why the same physics would operate with such wildly different strength at two opposite ends of time. Furthermore, the field would need a remarkably complex potential energy landscape, one with a steep cliff to power inflation, a long, flat plateau to lie dormant for billions of years, and then a gentle slope to slowly roll today. Crafting such a landscape can feel more like engineering a story than discovering a law of nature, yet the quest persists, fueled by the promise of a complete cosmic biography. Unifying these two great accelerations would mean that the universe's entire dynamic history, from its explosive origin, through the long ages of structure formation, to its current accelerating flight, could be told as one continuous physical saga. It would connect the first unimaginable moment to the distant future, revealing a cosmos governed by a consistent, if deeply hidden, logic. This represents the highest goal of the scientific imagination, to find not just answers but a story where every chapter, from the first word to the last, makes sense together. Amidst this whirlwind of creative alternatives, a powerful and pragmatic voice urges caution. It champions the cosmological constant, lambda, not as a placeholder of ignorance, but as the most honest and successful description we possess. This perspective argues for a principle as old as science itself, simplicity. When faced with a cosmic effect, should we not favor the simplest explanation that fits all the data, until that data definitively forces us to do otherwise? This is the essence of Occam's razor, a guiding light in scientific reasoning, and for Lambda's proponents, it cuts directly to the heart of the debate. The cosmological constant is mathematically the least complicated term you can add to Einstein's equations to account for acceleration. It is a single number, a fixed parameter that requires no new particles, no hidden fields, and no adjustments to the law of gravity. And against this stark simplicity, its empirical success is nothing short of breathtaking. The lambda-cold dark matter model, with this one constant value for dark energy, has passed every major cosmological test for over 2 decades. It matches the cosmic microwave background with exquisite precision. It correctly predicts the distribution of galaxies in the vast cosmic web. It aligns with the observed abundances of light elements and the timing of the first stars. In short, it works, and it works spectacularly well across independent lines of evidence that span the entire history of the universe. From this vantage point, the drive to replace Lambda with more complex constructs can seem premature, even indulgent. Proponents ask a pointed question: what definitive, unambiguous observation currently requires us to abandon the cosmological constant? The Hubble tension is intriguing, but it is not yet a verdict. It could be resolved by better understanding of local measurements or by small, subtle additions to the early universe, not by overthrowing our entire model. The desire for a dynamical explanation is understandable, but is it motivated by data or by a philosophical discomfort with a constant we do not fully understand? Every alternative theory introduces its own baggage. Quintessence fields require carefully engineered potential energy landscapes, which critics argue is just a different, and often more convoluted, form of fine-tuning. Modified gravity theories struggle to match all the successes of general relativity while introducing new theoretical ghosts or instabilities. Exotic fluids like the Chaplain gas often fail to match the detailed clustering of galaxies seen in our surveys. In the quest to solve one mystery, we risk creating several new ones, all without a clear observational mandate to do so. This conservative stance serves as a crucial counterbalance in the scientific process. It is the voice that demands extraordinary evidence for extraordinary claims. It reminds the community that while exploring the exotic frontiers of theory is essential and exciting, we must not mistake creative possibility for established truth. The universe, for all its wonders, might ultimately be described by an elegantly simple constant. The profound mystery of why that constant has the specific, tiny value it does would then be a puzzle not for cosmology alone, but for a deeper, future theory of quantum gravity. That search would continue, but it would be built upon a firm, empirically rock-solid foundation. The cosmological constant represents a humble acknowledgement. Sometimes the most powerful answer is to accurately describe what we see, even if the ultimate why remains for now just beyond our grasp. The phantom haunting our equations has also captured our collective imagination. Dark energy has quietly seeped into the stories we tell, from the grandest science fiction epics to the immersive worlds of video games. It appears not as a dry scientific term, but as a plot device of cosmic scale, a mysterious force that powers faster than light travel, threatens entire civilizations, or hides ancient secrets in the void between galaxies. This cultural adoption is more than just borrowing a cool name. It signifies a profound shift in our cosmic narrative. For millennia, our stories of the heavens were about gods, heroes, and familiar celestial bodies. Today, the dominant backdrop is a universe where over 2/3 of reality is made of something utterly unknown. Our modern myths are now woven with threads of dark matter and dark energy, framing a cosmos that is profoundly alien, governed by shadows we can only detect by their gravitational echo. This cultural footprint serves a vital purpose. When a teenager encounters dark energy in a video game or a blockbuster film, it sparks a question: what is that? That moment of curiosity is a seed. It can lead to a documentary, a book, a late-night internet search, and sometimes a lifelong passion for physics. By entering popular culture, this profound scientific mystery becomes accessible. It demystifies the idea that the frontiers of knowledge are locked away in dense journals, and instead presents them as the most exciting adventure story of all, the story of reality itself. This shared narrative also holds up a mirror to our time. Our fascination with these invisible cosmic forces reflects a deeper human condition. We live in an era of immense technological power, yet we are humbled by the realization that we understand only a tiny fraction of what exists. Stories featuring dark energy give that feeling a shape and a name. They allow us to grapple with the awe and existential unease of living in a universe where the dominant players are unseen and unknown. In doing so, they transform abstract cosmology into a relatable human experience, a shared contemplation of the ultimate mystery. By becoming part of our common language, dark energy transcends its scientific definition. It evolves into a powerful symbol. It stands for the endless frontier of human curiosity, for the thrilling truth that the universe is stranger than we can suppose, and for our species' relentless, beautiful drive to shine a light into the darkness, no matter how profound that darkness may be. The Nobel Prize in Physics has been awarded for less than the final answer. It honored the discovery of the acceleration itself, a monumental revelation that the universe's expansion is speeding up. To win a Nobel for explaining why it accelerates would require something even more profound. A definitive solution to the puzzle, one that moves beyond a successful model and into the realm of fundamental understanding. So what would that eureka moment look like? It might arrive as a single, unambiguous number from a next-generation telescope. Imagine the combined data from Euclid, Roman, and the Rubin Observatory finally pinning down the equation of state W, not as a constant, but as a value clearly and confidently different from -1, drifting over time. A 5 sigma detection of a dynamic W would be a direct experimental kill shot for the simple cosmological constant as a fundamental entity. It would be irrefutable evidence that dark energy is alive, changing, and something like a quintessence field. That measurement alone could be Nobel-worthy, as it would forever change the question we are asking. Alternatively, the breakthrough might not be a number, but the detection of a new force. If the quintessence field is real, it might not be completely silent. It could mediate a fifth force, a subtle interaction beyond gravity and electromagnetism that acts between ordinary matter. Finding even the faintest, most exotic signature of such an interaction in a lab experiment or in the precise orbits of distant stars would be a direct discovery of dark energy's agent, transforming it from a cosmic effect into a tangible part of particle physics. The Nobel would go to those who first designed the experiment to catch it. The most coveted prize, however, might be for a purely theoretical triumph. A lone physicist or a small team, armed with deep principles from quantum gravity or string theory, could one day derive the observed value of the cosmological constant from first principles. No fine-tuning, no arbitrary numbers, just a mathematical inevitability from a beautiful, unified framework. This would not just explain dark energy, it would solve the worst fine-tuning problem in physics and likely bridge general relativity with quantum mechanics. Such a theoretical leap would be instantly recognized as one of the greatest intellectual achievements in history. Or the answer could be so vast it redefines reality itself. Suppose a unique pattern is found etched into the cosmic microwave background, an imprint that can only be explained by our universe colliding with another bubble in a multiverse during its inflationary infancy. That signature would be empirical evidence for the multiverse, providing a statistical, landscape-based explanation for why our cosmological constant is so small. The Nobel here would reward those who predicted the signature and those who found it in the data, confirming a cosmos of unimaginable plurality. The path to this pinnacle is not merely about collecting more data, though that is the essential foundation. It is about the paradigm-shifting insight that makes all the disparate pieces click into place. The ultimate theory will need to perform a breathtaking triple feat. It must resolve the catastrophic fine-tuning of the vacuum energy. It must naturally explain the cosmic coincidence of why dark energy became dominant precisely as intelligent life arose. And it must be seamlessly compatible with, or even predictive of, a working theory of quantum gravity. This is the monumental challenge for 21st century physics, a puzzle that touches the beginning, the middle, and the ultimate fate of everything. The discovery will not just fill a blank in our equations, it will reveal whether we live in a universe of elegant simplicity, dynamic evolution, or unimaginable multiplicity. The greatest mysteries in the cosmos are not reserved for a select few. If the puzzle of dark energy has ignited a spark of curiosity within you, know that the path to contributing to this quest is more open than ever before. This is a field built on wonder, and it welcomes those who are willing to learn its language. Your journey begins with a strong foundation in the fundamental sciences. A deep understanding of physics is essential, of course, but it is a particular kind of physics. You will need to master the elegant, often counterintuitive principles of general relativity, the theory that describes the universe on its largest scales. Alongside this, a robust knowledge of quantum mechanics provides the crucial counterpart, the rules for the very small. These two pillars are the bedrock upon which all modern cosmology is built. But the bridge between theory and observation is built with mathematics. Proficiency in calculus, differential equations, and linear algebra is not just helpful. It is the toolkit you will use every day to translate the universe's whispers into comprehensible equations. Yet cosmology today is not solely conducted with pencil and paper. It is a science driven by immense datasets and colossal simulations. This means that alongside your physics and math, developing strong computational skills is non-negotiable. Learning programming languages like Python is a tremendous first step. The ability to handle, analyze, and visualize data is how discoveries are now made. You can gain invaluable experience by getting involved with the data from the very surveys we have discussed. Many large projects, like the Dark Energy Survey or the upcoming Legacy Survey of Space and Time, have public data releases or opportunities for student involvement. Analyzing real astronomical data, learning to spot the subtle statistical signatures of cosmic acceleration or the growth of structure is the most direct way to contribute to the front line of research. For those drawn to the theoretical side, immersing yourself in the literature is key. Start with foundational textbooks on cosmology and general relativity, then move to reading the key papers that define the field. Do not be intimidated by what you do not understand at first. Let it guide your learning. Actively seek out the community. Look for summer research programs at universities or national laboratories, which are designed to introduce undergraduates to real research problems. Attend departmental seminars, even virtually, to hear scientists present their latest work and see how the scientific conversation unfolds in real time. Reach out to professors or researchers whose work inspires you. A simple email expressing genuine interest can open doors. Remember, this is a vibrant and open field. The dark energy problem is a grand challenge precisely because it resists simple solutions. It demands fresh perspectives and innovative thinking. The next breakthrough could come from a novel way of analyzing galaxy clustering, a clever new test of gravity, or a theoretical insight that connects disparate pieces of the puzzle. That insight could very well come from a student who is just now beginning their journey, someone who looks at the same data everyone else has seen, but asks a question no one else has thought to ask. The phantom of the cosmos is waiting, and it will be the next generation of curious minds who finally bring it into the light. Our search for a phantom force is also a search for our own story. The true nature of dark energy will not just fill a blank in a textbook, it will write the final chapter for our cosmos and define humanity's place within that grand narrative. If dark energy is indeed Einstein's simple cosmological constant, then the universe's fate is sealed in a quiet, chilling certainty. Billions of years from now, long after our sun has faded and the Milky Way has merged with its neighbors, the relentless, gentle push of Lambda will continue unabated. Galaxies beyond our local gravitationally bound group will vanish over the cosmic horizon, their light stretched beyond detection. The universe will grow colder, darker, and emptier with each passing eon, destined for a vast, silent, and profoundly lonely expansion. In this vision, we are temporary witnesses to a brief, bright flare of structure in an otherwise empty and fading arena. Yet if dark energy is something dynamic, like a rolling quintessence field, the future becomes a mystery once more. Could this force weaken over time, allowing gravity to regain some sway? Could it strengthen dramatically, hastening an end? Our cosmic destiny would then be part of an unfolding plot, not a foregone conclusion. This possibility restores a sense of narrative to the cosmos, a future that remains unwritten and dependent on the hidden physics we are now striving to uncover. This profound uncertainty touches the very heart of why we look up. The monumental effort to understand dark energy is not a detached academic exercise. It is the latest and perhaps greatest chapter in the oldest human project of all, the struggle to comprehend the universe we find ourselves in. We are the species that learned to read. Not just words on a page, but the subtle codes written in the light of distant galaxies, the faint whispers from the cosmic microwave background, and the silent mathematics of space-time itself. Each measurement, each supernova carefully catalogued, each massive computer simulation is an act of reading the cosmic story as it reveals itself to us. This endeavor does two powerful, seemingly contradictory things to the human spirit. First, it humbles us utterly. The evidence is unequivocal. The stars and planets and everything we see and touch constitute less than 5% of reality. The dominant components of the cosmos, dark matter and dark energy, are completely invisible and unknown to us. We are not the center of the universe. We are not even made of the same stuff as most of it. We are a rare and delicate phenomenon living on a fragile planet during a fleeting moment of cosmic balance. Yet simultaneously, this quest empowers us. For all our smallness and ignorance, we have developed the reason, the tools, and the sheer stubborn ingenuity to detect these phantoms. We have built telescopes that act as time machines, peer back to the first light, and designed experiments that listen for the ripples in spacetime from colliding black holes. We are using the laws of physics discovered in our tiny corner of existence to decode the behavior of the entire universe. This is a breathtaking act of confidence. It means that the human mind, through careful observation and relentless curiosity, can push back the boundaries of the unknown, no matter how vast or dark those boundaries may be. In the end, the search for dark energy is a search for meaning itself. It asks whether we live in a cosmos of elegant, fixed simplicity or one of dynamic, evolving complexity. It asks whether our future is a quiet fade or an unpredictable tale. But most of all, it reaffirms that we are here, right now, capable of asking these monumental questions and daring to seek their answers in the deep, silent night. The landscape of cosmic explanation is vast, and every path leads to a deeper question. We have wandered through territories of thought, from a constant woven into space itself to rolling fields of quintessence, from rewritten laws of gravity to universes projected from their boundaries. Each brilliant framework is a testament to the same driving force, our need to understand why the cosmos is flying apart. The standard model, with its simple lambda, fits the observational tapestry of our universe with stunning precision. Yet its very success highlights the profound theoretical abyss beneath our feet, the catastrophic fine-tuning, the eerie cosmic coincidence, the silent phantom commanding 70% of everything. These are not small cracks. They are chasms that guarantee the competition of ideas is not just academic, it is essential. The coming decade will transform this theoretical debate into an empirical verdict. A flood of data from observatories like Euclid, Roman, and the Rubin Legacy Survey will pour in, measuring the universe's expansion and growth with a precision we have never known. This is not merely more information, it is a new kind of vision. These instruments will measure the subtle personality of dark energy, its equation of state, with such clarity that we may finally see if it is a fixed constant or a changing entity. They will map the cosmic web in such detail that we can read the history of its suppression by this repulsive force. The theories we have explored today are not just stories, they are specific predictions waiting to be confirmed or shattered by this incoming light. One of them, or perhaps an idea not yet conceived, will emerge from this trial by data. This search transcends abstract science. Dark energy is not a remote curiosity for specialists. It is, by every measure, the dominant component of reality. It holds the pen that is writing the final sentence of our universe's story, determining whether the grand finale is a silent fade, a gradual unweaving, or something beyond our current imagination. To pursue its identity is to engage in one of humanity's oldest and most noble endeavors, to look into the unknown and insist on finding a pattern. It is a quest that humbles us with our ignorance, even as it elevates us with our ingenuity. The phantom in the void challenges us to think bigger, to question our most fundamental assumptions, and to remember that the greatest discoveries often begin not with answers, but with a breathtaking mystery. If this journey to the edge of understanding resonated with you, there are countless other cosmic frontiers waiting to be explored. Consider subscribing to stay curious with us. And we would truly love to know which of these competing visions of reality feels most compelling to you: the constant, the dynamic field, the revised gravity, or the multiverse. Share your thoughts below. The conversation about our cosmos is just beginning.